All right, so this is going to be a video about optimization, and optimization is basically finding the worst case scenario or best case scenario of whatever you're looking at. So that's kind of how I want you to frame all of this optimization is you're thinking about the min or the max of something. So maybe you're looking for the max profit or the minimum cost or that sort of thing. It's similar to the relative extrema and absolute extrema stuff that we covered previously in the previous section, but this time it's going to actually be linked to real world things. So that's what optimization is all about. The enduring understanding here says a function's derivative can be used to understand the behaviors of a function. So again, we're going to be using the fact that the derivative tells us what the behavior of the actual function is doing. So a function's derivative tells us what the original function is doing. The learning objectives right here, it says calculate the min and maximum values in applied context. So again, it's back to that min and max stuff, only in real world stuff. And it says interpret min and max values calculated in applied contexts. Okay, so not only do we have to calculate them, we have to interpret them and make sure they mean what we want them to mean. The next one, the derivative can be used to solve optimization problems. Okay, so we're going to be using the derivative to solve these problems, which makes sense. This whole unit is about the applications of differentiation, applications of the derivative. So that's what we're going to be using it for. That is finding the min and max value of a function in a given interval. And then it says right here, minimum and maximum values of a function can take on specific meanings in applied contexts. Okay, so you might have one where it's a min and one where it's a max, and it means different things depending on the scenario that we're looking at. So those are the main things that we're going to be covering in this section. All right, 3.3.3 optimization. It says optimization is basically finding extrema in the real world. I kind of already said that. So it's basically we're going to be repeating the same steps that we did in that one section where we went over extrema. Namely, so say we're trying to figure out the min or max of something. Step one is find the derivative. Step two is find the critical numbers. All right. Step three is to make that critical number line and test the intervals. So critical number line into testing the intervals. And then that's basically all the steps. Step four would be to solve and use those. Once you test the intervals and you know what the answer should be based on those. And that's basically where we're going to be going from there. All right. Keywords that you're going to want to look at when you're doing optimization, things that you're trying to look for, make sure you understand what you're looking for. So for the maximum, sometimes they use the terms like maximize, the most, the greatest, the fastest, or the furthest. Okay, those would be finding the max of something. Where the minimum, it's something like minimize, least, smallest, cheapest, closest, that sort of thing. Those are all examples of when optimization is used to find either mins or maxes. It's pretty straightforward. It shouldn't be too confusing, but just make sure you understand that. And then let's do our first example here. So it says, you are tasked with creating a fenced-in rectangular area for cows to graze in. So step one when doing this, I'm actually going to just draw this out. So I'm going to draw a rectangle. It doesn't have to be to scale or anything like that because we're trying to figure out what's going on in this scenario. So I'm just drawing a rectangle. Fenced-in rectangular area for cows. So cows are going to be, grazing in here. The farmer that hired you wants to maximize the area. So that is the first thing we're looking for here, maximum area. We're trying to figure out what's the most area you can have in this rectangle. And it looks like possible for this area, but can only afford 500 feet of fencing. So all around that red rectangle that I made, basically we're trying to figure out, you only have 500 feet of fencing there, so the perimeter can only be 500 feet. What would be the maximum area for that, given that it has to be a rectangle? It says, what dimensions should the area be used to maximize the area, and then what is the value of that maximum area? So we're trying to figure out the length and the width. Let's just call this the width and this the length here, which means this is also the length and this is also the width here. We're trying to figure out what is the L and the W for that first section right here. And then we're trying to figure out the actual area for that second one right there because it says what's the maximum area. All right, step one when doing this is figuring out the derivative. Okay, I kind of was talking about the steps in this previous slide over here. So step one, find that derivative. Now, the derivative is whatever we're actually trying to maximize or minimize. In this case, it's maximize. So we're trying to maximize the area. That means we have to find the derivative of the area. Okay, well, we know the area is just going to be equal to length times width, but we need to figure out a prime of this, so the derivative of this. But the problem is we have two variables, and you cannot have two variables when you're finding mins and maxes. It just opens up a whole other can of worms. Somehow we have to get it where that's only it only has one variable. Okay, and the way to do that is using this 500 feet of fencing fact right here to know that basically the perimeter is equal to 500 feet, which is also equal to 2L plus 2W, because you could just add up all of these sides. It all has to equal to 500. And what's great about this is it allows us to solve for L or W. In this case, I'm actually going to solve for W. It doesn't actually matter. But first thing, I'm going to divide everything by 2. So now we have L plus W is equal to 250. And I'm going to solve for W. So W is equal to 250 minus L. So now what we can do is substitute that W right here for this W here. And now we have an equation that only has one variable. So it's a way easier derivative to mess with compared to when there's two variables. Okay. First thing I'm going to do, I just realized this was actually not the derivative, it's just still A. We have to take the derivative of that, but first we have to distribute. It's going to be 250L minus L squared. Now we can take the derivative. Okay, so step 1 is figuring out what you have to take the derivative of. And the easiest way is whatever you're trying to minimize or maximize. In this case, we're maximizing area. Whatever you're minimizing or maximizing, that's what you're derivatizing. That's how I always remember it. So we're finding max area. That means a light bulb should be going off in your head. We got to take the derivative of area. But first, we need an area formula. So that's what we did right here. Now that we have this area formula, let's take the derivative of it. And you get 250 minus 2L. Okay, the next step was find the critical numbers. So I'm going to set that equal to 0. You do not have to worry about undefined on this one because it's the real world. So that's one reason you don't really have to worry about doing anything with undefineds. And secondly, it's linear, so it's not going to have any division by 0. So you don't have to worry about any undefineds in this. We're going to solve this, and L is equal to 125. Okay, but you need to actually test the interval to make sure this is a maximum. What if this 125 is really a minimum? You have to make sure, you have to test out the intervals to make sure. So that's what we're going to do. We're going to draw critical number line. I'm going to put 125 on it. All right, and it's going to tell us what the area, this derivative is going to tell us what the area is doing. So what we need to do is plug in a value between 0, so this is a 0 right here, and 125, so maybe just plug in 1. If you plug in 1 to this derivative right here, you are going to get a positive because it's 250 minus 2. So that means the area is going to be increasing. Plug in, I don't know, infinity or 200 or 150, it doesn't matter. If you plug it into the derivative right here, you are going to get a negative value. That means it's decreasing. So if you were going to draw the function, this a prime function, it's going to be increasing 0 out at 125 and then decreasing. So you know that it's actually going to max out right there. You know that 125 is the max dimension for that L anyway to get you that value. So now that you've tested it out and proved it there, we have our L. That is definitely the answer. I'm going to put it in feet because this is all in feet. But you have to find both dimensions, so that means we also have to find the W. Well, what's great is we already have this W equation right here where it's just 250 minus L. So that's just going to be 125 as well. You don't need to test that because the L already gave us that max. So it's just 125 by 125, which makes sense that it's a square to get the maximum area. The next bullet point says, what is the maximum area? So what we have to do is use that area formula that we have right here, length times width, to figure that out. So it's just going to be 125 squared. And the max area, so I'm going to write that right here, the area of the max is going to be 15,625 feet squared. And again, I found that by just multiplying the L and the W, so that's the max area. This is the max dimensions right here. And that's the answer for this problem here. Okay. Now you might have guessed, oh, it's a square. It makes sense that it's a square right away. But you know, I just kind of like to show, I like to start optimization with this problem because it kind of just shows how all this works. Even if you would have guessed that it's a square, it still shows that how it works. And I don't know, just a good problem to get your feet wet with. Before we go on to a little bit more of a hard problem here. So example problem number 2, it says, now you're tasked with creating a fenced-in rectangular area for cows to graze in, same as before, but the farmer that hired you wants the maximum area possible again, but can only afford 500 feet of fencing again. But you come up with the bright idea of setting up an area next to a river so cows can drink from it. So basically this time, your fenced-in area is going to look like this. So there's that rectangular area there, and it's right by water, so we're going to act like the water is right here. So here's where the stream of water goes. There's the fenced-in area. Let's see here. We still have a width here and a length here. So you basically just got rid of one of the sides. Okay, now it says, what dimensions should the area be to have the most area for the cows if the river can be used as a side for that area? So now you just basically got rid of one of the sides. So it saves you on some of that fencing. And we're just basically trying to figure out what is the most area. So most is the key word here. So again, we're going to have to take the derivative of the area, and then what eventually is the maximum area. So we find those dimensions that give the max area, and then we actually find what the max area is as well. Okay, some things don't really change in this problem, namely the area formula is still the same. So it's still length times width, but the perimeter changed. Okay, the perimeter is still 500, but now it's 2L plus W. So we got rid of one of those W's here, so it's just 2L plus W. And what I'm going to do here is I'm going to solve for W again, and I'm going to throw it into this W right here so that we have one variable. It's just going to be 500 minus 2L. So now our area formula becomes L times 500 minus 2L. And before I started this problem, I really should have said, guess, like, how much more area do you think you're going to get if you get rid of one of the sides? It's awesome to do that kind of thinking because it's not intuitive. But the answer is at the end, it's not going to be intuitive. You're going to go, oh, I would have guessed that. It's kind of weird to think about what the final answer is, but it's kind of good to guess at the same time. Are you going to have 10 times as much area? Are you going to have 100 times more area? Are you going to have the same exact area? What actually changes on this? So it's kind of a good question to do before you start this. Just a good question to think about. But anyway, we're going to have that area volume. Area. So we're going to have that area equation right there. And we have to do the derivative of this. And you end up with something like this. Okay, we're going to set this equal to 0 and solve. So we're going to add 4L to both sides, divide both sides by 4, and you're going to have L is equal to 125 feet. Again, how is that possible? We just got rid of one of the sides, yet we end up having the exact same value. That doesn't really make much sense, does it? Well, it does, but I haven't shown you that part yet, so it'll make more sense in a second. But first thing we got to do is actually test this out. Does this actually yield a max? So that's what we're going to do right now. So let's plug in a value like 1 in there. It's definitely going to be positive, so that means the area is increasing. Plug in infinity, you're going to have a negative there, so it's decreasing. So we still have the max there, so that's good. But it still maxes out here, so it's going to go up and then down. That's what the function looks like. But we need to figure out the other dimension for the W. Well, W is equal to, we have a W equation right here that we can use. And if you plug in 125 to that, you're going to get W is equal to 250. So now the W actually multiplied by 2 from before. If you remember the previous problem, it was 125. Now it's 250. So basically the width the width doubled. Now if the width doubled, that means your max area also doubled. Because remember, it's length times width. So now your area max is going to be equal to 31,250 square feet. Okay, so this is kind of weird. This is why I wanted you to kind of guess, like, what happens if I get rid of one of the sides? Because I've never had a student to actually just go, oh, it's going to double. Exactly. It just makes sense. You get rid of one side, the whole area is going to double. It's not very intuitive to think that way. So that's why I kind of like showing this problem. You have to do a little bit more work. The perimeter equation changes. But if you notice, it's still the same thing. Find the equation, find the derivative of the equation, find the critical numbers, test the critical numbers on the critical number line, make sure it's a max or a min, and then figure it out from there. So anyway, that's example problem number 2. Okay, those were both involving area. This one is all about minimizing the cost to build a box. Zoom in a little bit here. So minimizing cost to build a box. We want to construct a box whose base is a square. So the first thing I'm going to do here is actually just draw this out. So the base of this box is a square. It's a square, so I wrote x by x on the bottom there. That's why there's 2 x's there. There's a height to this box, so I'm just going to put an h there. The material used to build the top and the bottom costs $8 per square foot. Okay, so let's see here. The cost for the top is equal to the cost of the bottom, which is equal to 8 times the area, because it says per square foot, so it's going to be 8x squared. So both of those are 8x squared. All right, the material used to build the sides, so the cost of the sides is going to be $6 per square foot. So that's x times h. So it's just $6 times x times h for that. It says determine the dimensions that will minimize the cost. So we need a total cost now We have these costs here. So the total cost is going to be equal to 2 of those tops, because there's the top and the bottom. So 2 of the top and bottom. So it's going to be 16x squared, because there's 2 of those, plus the sides. Well, there's 4 of those sides, times the 6 times x h. Okay. Now, just like before, we have 2 variables. We cannot have 2 variables, so that's a problem. So one thing I did not write down is the volume of this thing has to be equal to 36 square feet, or cubic feet, I'm sorry, it says 36 cubic feet, which is equal to x squared times h. Okay, this blue equation that I just wrote is going to be your ticket to making it so there's only one variable for that cost equation. So we're going to solve for h. The reason I solve for h is because there's just one of them right there. It's easier. There's an x squared and an x here. So then you'd have to babysit more things. So I just kind of went with the h because it's easier. It doesn't matter which one you do. You'll still get the same answer. But I advise doing it the easiest way possible. So we have 16x squared plus 24x times 36 over x squared. Okay, I'm going to simplify all that down. So now your cost equation, again, we still have to take the derivative of this, but we have to make the equation first. You're going to get 16x squared plus, well, I could simplify this right here. These cancel. So now you're just going to get 864 divided by x. So I'm just going to write x to the negative 1. Okay, from here, I'm going to do the derivative. So you get 32x minus 864 x to the negative 2. And we're going to set this equal to 0 to find those critical numbers, or undefined, but you don't need to worry about undefined because this is a real world problem. There's no division by 0 in the real world, so we're not going to worry about that. To solve this, we're dividing by x to the negative 2 here, so I'm going to multiply everything by x squared. So do that, and then 864. The x to the negative 2 is going to cancel if you multiply it by x squared, and you end up with something like this. Divide both sides by 32, so that'll be x to the third minus 27 is equal to 0. Add 27 to both sides, cube root both sides, and you end up with x is equal to 3. Okay, now we need to actually figure out, is this actually a min? The other ones we were doing, it was like a max volume. This one, you have to figure out if it's a min. Also, one thing that I want you to notice is I put 0 here. You can't have negative dimensions for this, so that's why I started with 0. It's not part of the domain to have negative numbers, so that's why I started at 0. We're going to do the cost derivative, tells us what the cost is doing. Plug 1 into the derivative here, you're going to get negative. So I'm going to put a negative here. So that's decreasing. Okay, plug in, I don't know, a value like 5 or something like that, or maybe 10,000, doesn't really matter. This is going to end up being positive. So that's positive here, so it's increasing. So the function, the cost function, would basically be doing a decreasing, flatlining, and then increasing here. So it definitely is a min. Okay, so 3, in this case, it's going to be 3 feet, is going to represent the min. For the x, we still have to figure out the h. We have an h equation. Let's see, where's that h equation? Right here in purple. So we're going to throw in the 3 in that. So it's 36 divided by 9, so that's going to be 4 feet. So that's the height. Okay. It says determine the dimensions that will minimize the cost. That's all we're finding. We're not actually figuring out the cost, but if you wanted to, you could put that x value and that y value into that cost equation right here, and you would end up with that. That's the answer for the actual minimum cost, but it's not asking for that. It's just asking for that dimensions. Now you can kind of see how this is applied in the real world. If you are building a box and there are certain costs applied to it, you want to minimize that cost as much as possible, but you still have the constraint that you want it to hold 36 cubic feet. Okay, so you can see how a company would want to actually do the math and figure out the dimensions to use for this that is going to yield the most amount of money saved. So if you minimize the cost, you're saving more money. It makes sense why a company would want to do that. All right, let's go to the next one. Okay, oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. Okay, so now we're going to have to try to draw this. This will be interesting. You have some kind of lake here, and there's a pipeline down here with oil, and it's leaking the oil out this way, and it's going at a rate of 2,000 cubic centimeters per minute. Okay, so that's already a rate. That is important to understand. It's already a derivative if you want to think of it that way, this 2,000. Okay, and it's forming, some kind of oil slick here on the water. Pardon my drawing, it's terrible, but you get the idea. a recovery device arrives on the scene and begins removing the oil. Okay, so some device goes in here and starts removing the oil. So now the oil is going away. Actually, I should have it going away like this. And it's going away at a rate of R of t, which is applied using this equation right here. R of t is equal to 400 root t cubic centimeters per minute. Okay, so that's a derivative as well, whose t is in minutes. Since the device began working, okay, find the time t when the oil slick reaches its maximum volume. Okay, one thing to note on this is that the units here are cubic centimeters and then another cubic centimeters per minute. So it's already volume, it's a volume rate. So essentially what you have here is a rate in and rate out problem. So the total rate of the volume, that's what this T is going to represent, the total rate of the volume is going to be, so it's 2,000 minus whatever R of T is. Okay, so this is the amount that's there, minus whatever is removed. So it's the amount that's being added minus what's being removed, all with respect to T. The 2,000 is just a fixed rate, it's a constant rate, so you don't need any T's with it. But the important thing to understand is this is already a derivative. So all you have to do is technically just set this equal to 0 and solve. You don't have to do any derivative because it already is a derivative. So what we're going to do is I'm going to add R of t to both sides, but I'm actually going to put in 400 root t. And we're going to solve for t here. Divide both sides by 400. You get 5 here. That cancels away. Square both sides. And you get t is equal to 25. Let's see, it's in minutes. Okay, but you need to test. Is this actually going to yield the min or the max volume? All right, so we need to figure out the time, the total rate right here, this T, capital T of T, and it's telling us what the volume is doing. And we're at 25 here. Okay, let's plug in a value like, 1 into the derivative. So if you plug a 1 into this derivative here, it's 2,000 minus 400, because R of t is 400 times square root of 1 is 1. So that's going to be a positive. Again, you don't really need the number necessarily. You just need to know whether it's positive or negative. And then plug in another value like, a million. If you plug in a million, this R of t is going to be greater than the 2,000, so it's going to be negative. So that means this is decreasing. Okay, so this is definitely going to be the max, because if you actually graph this out, it's increasing and then it's decreasing. So that's what the volume is doing. The volume's increasing and then decreasing, so that is the maximum volume. So it says find that the time t that has the maximum volume, that would be this answer right here. T is equal to 25 minutes. So that's basically a video on optimization with some example problems. Hopefully that helps make the concept make a little bit more sense. If you have any questions on anything in this video, let me know.